Now we will move on to the extraction of the metals individually. After going through all the processes, now we'll go to the individual metal extraction processes. First, I will talk about silver. Silver, of which ores are silver, Ag2S silver glance, it can be AgCl, it can be the ruby silver. So Ag2S silver glance, AgCl, Ag2S, Sb2S is ruby silver we call. And we take the MacArthur forest process, in which we basically take Ag2S ore, froth flotation, so that we can increase concentrated ore, because we know that froth flotation is applied for sulfide ore, and here there will be little silica. After that we take a 5% NaCN and air, we purge and filter. If I filter, then we get NaAgCN twice, and the impurity will be separated out. And then this sodium argentocyanide, or we can say sodium dicyanidoargentate 1, this complex is treated with zinc powder. Of course, there will be silver deposition and zinc will be in the complex. And now this silver is impure. This will be electrorefining process. This will be passing through electrorefining process. We can get silver pure. And the impurity is zinc, copper, and gold with the silver. So this is the way by which we produce silver. So this is the loop. I have drawn the diagram in the loop diagram. So there are the flowchart diagram, so that you can remember very well and very effectively. So therefore, only thing, yes, we added sodium cyanide over here zinc we have added, that's it. And froth flotation is a common process for the sulfide ores concentration. Next we will go to the gold. Gold, basically we take the ore, it is a native ore basically, or it can be sulfide ore. If it is sulfide ore, then directly we can go, it is native ore basically. Gold, it is native ore. It is treated with sodium cyanide dilute, so we get this, and plus oxygen of course, and then we get NaUCN twice, where gold is +1. This NaUCN twice when treated with zinc, again we get residue crude of gold and sodium zinc cyanide complex, that is the sodium dicyanido zincate 2 complex. And then the residue crude ore basically have got basically the impurity. So the impurity to be removed as this way, that we first go to the, this is a gold basically, this is a gold, and gold having lead impurity can be removed by cupellation or cupellation process, where lead basically removes out and oxygen basically reacts with lead, not with gold, and lead is removed by PbO2 formation, PbO formation or PbO2 formation. And then gold, which is again impure, having contains impurity, and silver, copper are the impurity. So parting process we do, and it is concentrate sulfuric acid we apply, and heating, the copper and silver will go and will get gold pure. Basically gold pure will get gold pure. So this is the way, that means we are using cupellation, that is you use cupel or bowl basically, in which the molten metal will be there, in which oxygen will be purged, and of course lead oxide will, PbO will go out, and our PbO2 will go out, and then we get gold. And this gold with impurity 1 second, copper and the silver we can remove by parting process using constant sulfuric acid and heat. Gold will be not reactive and therefore unreactive, so this is pure gold can be found out. So this is a flowchart diagram for the gold preparation. Next we can go to the tin. Tin for which we use basically SNO tin stone. The tin stone is the ore basically have got wolframite ore, that is FeWO4 MnWO4, and that is tungsten compound. And then magnetic separation, if we remove this, we can remove this basically, and then some silica is there that can be removed by gravity separation, and then we get concentrated ore. Of course there will be definitely some little silica also. Now it is roasted with oxygen. If we roast it with oxygen, the copper will copper to copper oxide, ferrous oxide, and the sulfides, copper sulfate, ferrous sulfate will be obtained along with the SNO2. Now what we do is that washed with hot water. If we use hot water, copper sulfate, ferrous sulfate dissolved by the copper oxide, if you SiO2 and SNO2 will be still remaining, and then we will go for magnetic separation. If we go for magnetic separation, iron copper will be going out and SNO2 will be there. Then after that carbon reduction we can apply, so that reaction can be taken place. SNO2 plus C will give you Sn plus 2CO basically, SNO2 plus 2C, Sn plus 2CO, tin will be obtained. And then of course tin has got the impurity. By liquefaction or sweating process we can get tin, which is basically not 100% pure, or we can't get also 100% pure. Anyway, 99.99% we can reach. So over here impurity iron plus copper oxide plus tungsten, and with this tin, and liquefaction, by liquefaction we get tin, and then with some impurity, and then again further refining by electrorefining, polling and then electrorefining, two processes, polling and electrorefining process. Already we have discussed the processes by which we can get 99% tin ore almost. So therefore again I will just, for your understanding, first the oxide ore is there, then magnetic separation, we remove the wolframite ore, and then silica will be there. Silica can't be removed to magnetic separation, then concentrate ore is just roasted, and then we get all oxides and sulfates, then washing with hot water so that you can remove copper sulfate, ferrous sulfate, and then oxides are still remaining, and then we'll go for magnetic separation. The magnetic material is removed, then SiO2 we get, at SiO2 we get, and carbon reduction we get tin, and tin have got impurities, and for the removal of impurities like iron, copper oxide, tungsten, we go for liquefaction or sweating process, and then we can go for polling and the electrorefining, so that 99% tin we can obtain. Next, if we talk about magnesium, magnesium is very difficult to get magnesium chloride, we know, because MgCl2 6H2 always hydrolyzes upon heating MgOHCl. So therefore in dry HCl condition we get MgCl2. For example, we take the carnallite ore KCl MgCl2 6H2 after water solution, after addition water solution will be there, and solution is cooled, KCl will crystallize, MgCl2 will be in the solution, then we can get MgOH2 precipitation, and then dry HCl will give us MgCl2, then electrolytic reduction we can get Mg. The reaction is Mg plus 2 electron Mg, it appears in the cathode, and of course MgO plus C plus Cl2, MgCl2 plus CO. This can be another process by which you can produce pure magnesium chloride, and molten condition, molten magnesium chloride when electrolyzed will get magnesium. There are two more processes, one is pre-gen process and thermal process by which also you can get magnesium. So this way we can see that these metals can be extracted, like over here we have discussed gold, silver, tin and magnesium. Of course gold and silver also undergoes the process called the hydrometallurgy, that is where we don't get anything. This part you can see, this is the hydrometallurgical part. Basically this is the hydrometallurgical part where, you know, it happens in the aqueous solution only, no heating or something like is there. Over here it is also hydrometallurgical part. This is a hydrometallurgy, or we can say leaching also, hydrometallurgy, or we can say leaching also. We can say leaching basically we use for the concentration. So over here it can be equivalently said as leaching also. So these are the processes by which we produce gold, silver, magnesium and tin. So we'll go to the next metals. Okay, my dear friends, now we'll go for the aluminium extraction. And you know, aluminium is a very important metal for our civilization. The aluminium has got reach to everywhere, starting from the aeroplane making and then spacecraft and everywhere. We use duralumin, one alloy basically, and in that aluminium's participation is very important to us, and is very costly. And you know, the pure aluminium sheet, if you want to frame, it will be always having the alumina, and there is Al2O3 oxide coated on this. So of course that the aluminium is very resistant to further reaction. So alumina coating is very inert in kind of nature. Now how do we get aluminium in the industry? First we go for the concentration of the mined ore like bauxite, or it can be gibbsite, or it can be diaspora, etc. For example, the ores can be bauxite, gibbsite, 3H2O, bauxite is 2H2, diaspora, and then cryolite, it is Na3F6. Generally we use in the extraction process from the alumina, and corundum is Al2O3. Now we have two kinds of bauxites in nature. One is red bauxite, another is white bauxite. Red bauxite and white bauxite. Red bauxite contains Fe2O3 as a major impurity, remember, that is a metal oxide, and whereas the white bauxite has got SiO2 as a major impurity. Other than that, Al2O3 2H2, it is the oxide, that is a bauxite, and SiO2 TiO2, both the cases will be there. And first, red bauxite has got Fe2O3 basically as the major impurity, and in the case of this SiO2, that is white bauxite, we get SiO2 as a major impurity. Now three processes we have chosen. One is Bayer's process, another is a Hall's process, another is a Sarpek's process, by which you can pure, you have to get pure Al2O3, because in the nature whatever we got Al2O3.2H, that has got a huge impurities, like as I said, SiO2, TiO2 and Fe2O3, etc. So therefore we have to remove those impurities basically. How do we do this? For example, Bayer's process, we take red bauxite in large vat, basically is called basically autoclave also, you can see, in which we basically digest with NaOH. Before that we just go for red bauxite calcination, in calcined ore, of course, the in presence and absence of oxygen, we do a little amount of oxygen, calcined ore, and then this calcined ore treated with 50% nearly NaOH and 150 degrees centigrade and 75 to 80 pounds pressure. If we apply in an autoclave and filter, we get two things: one, residue impurity, that is with Fe2O3, TiO2, etc. Another is NaLOH4 and Na2SiO3, sodium aluminum complex, basically with OH minus. And then this complex is now treated with diluted and with ample amount of water, excess amount of water, and CO2 is passed through the solution so that we can get AlOH3. And after heating AlOH3, we get at around 1100 degrees centigrade, we get Al2O3 pure. So our destination was to get pure Al2O3. Although we got from the nature Al2O3.2H2, but so many impurities are there, we remove it. So we have removed it and we have got Al2O3 as a pure. This is one way of doing that. You remember, always we are purging CO2 in all the process we will see, but CO2 basically, see, initially we use NaOH, now we are using CO2. That means CO2 basically neutralizes the excess NaOH, and so that because CO2 in nature it is the acidic oxide, so it will naturally they remove the excess OH minus and makes such a condition that we get AlOH3 precipitation, because excess OH minus gives AlOH4 minus, excess H plus gives Al plus 3, but we need AlOH3. So it is a CO2 is wonderfully control the pH of the medium so that we can get AlOH3, and then finally heating Al2O3. Secondly, we got the process Hall's process. This is also another process where red bauxite we choose, again as in Beer's process. It is heated at 1100 degrees centigrade first in presence of Na2CO3 and little CaCO3, and water excess we add on that. So of course we will be getting certain other impurities like Fe2O3, TiO2, etc., Fe2O3, TiO2, etc., and we get the soluble complex is AlOH4 minus, and then consequently CO2, if you supply and filter, of course the sodium carbonate solution will be in the filter, will go out and will get AlOH3 precipitation. This AlOH3 precipitation, again upon heating at 1100 degrees centigrade, we get Al2O3 pure. So you need to get Al2O3 pure, so you have got. Next we are going to Sarpex process. It is another process where basically we use white bauxite. Over here we use white bauxite, very important, white bauxite, and in the white bauxite we are heating at 1900 degrees centigrade in presence of coke powder and nitrogen gas, so that we can get aluminum nitrate Al, where aluminum is plus 3, nitrogen is minus 3, and we get CO and Si vapor goes out. These are basically all gases goes out, and aluminum nitrate and impurity. Of course, if we use NaOH solution, then of course Ln will give you NaLOH4 plus NH3 ammonia evolution, and impurities will be there, will be separated out as a solid. So in the filtered we get NaLOH4, and then again CO2. Again you have to use CO2 and huge excess of water, so you get AlOH3 precipitation, and then upon heating at 1100 degrees centigrade we get Al2O3. So if you see, this again pure Al2O3, you can say pure. It is also pure alumina. It's pure alumina, you can say pure Al2O3 means pure alumina. So what are the reactions involved in the Sarpex process? Very wonderful. You can see that Al2O3 plus C plus N to Aln plus, a very very important reaction for the studies of your 11-12. And this Aln plus NaOH plus H2 will give you NaLOH4 plus ammonia evolution. And of course if you use CO2 over here, then of course you are using CO2 over here, so in that case AlOH3 will be precipitated out, and further heating at 1100 degrees centigrade gives us Al2O3 as shown in the diagram. So this is the flow chart how to prepare the pure alumina, because alumina is the material which finally will be electrolyzed or electrolytic reduced process, we can say electrolytic reduction process, and the Al2O3 will be undergoing electrolytic reduction process very soon, and soon we will be showing that. So Al2O3 we have prepared, and now we will be going for the electrolytic reduction of alumina.